good. Is where we're going to start off. A glass of water. Actually, I'm going to go to the bathroom real fast. All right, so hopefully that fixed things. Yeah, it's a matter of a ground loop because my audio setup's all it's all wireless, and the receiver's actually out of battery, so I have to charge it right now. But if I charge it off of something that's connected to the computer, okay, good. It's gone. But if I charge it off of something that's connected to the computer, you get what's called a ground loop. And there's some interesting physics in that, even because basically what you're doing is you're setting some potential for the charging, but simultaneously you're connecting that to what you're transmitting into. So yeah, that's actually why you end up getting that kind of feedback there. So first question is one that Eric had, and it was on the final exam from 2016. So let me start recording this so I can upload this a little later. So the first question was one that Eric had, and this was you have this type of setup here where you have some rectangular loop of wire that has some width and some height, and there's some current that flows here. This is going to be some I0, and this starts out at some distance d away from here. But you're told that the loop moves away from the wire with some constant speed v0. So this is going to be moving away with some constant speed v0. And what we want to do is we want to find what the current is that's induced in this loop of wire. Okay. So in order to do that, we know that we're going to need to use Faraday's law. So the integral of E dot dl is going to be equal to minus partial derivative with respect to time of the integral of b dot dA. And so when we look at Faraday's law here, we realize that we're going to need to calculate what the time-dependent magnetic flux is here. So we're going to ultimately need what B is. And so in order to do that, what we're going to do is apply Amperes law. So Amperes law says the integral of E dot dl is going to be equal to mu naught times I in. And the reason why I'm doing that is we want to find the flux that passes through this loop, or the magnetic flux that passes through this loop. But in order to do that, we need to know what the magnetic field is. And to find the magnetic field, we know that there's some current that flows this way. And so we can calculate what the magnetic field is from Amperes Law. Okay. So what we can do is we can draw some Amperian loop here. This is going to go around like this. So it's going to go around this way. Sorry, this is not an E dot dl. This is a B dot dl. Okay. So integral around this loop of B dot dl is going to end up giving me a B times 2 pi r, which is going to be equal to mu naught times I in. So we can solve for this magnetic field, and then B vector is going to be equal to mu naught I0 divided by 2 pi r, because this I0 is going to be the current that's passing through the loop. Now I wrote a vector sign here, and typically what I'll end up doing is saying that this is some theta hat. But we need to know what the direction of the magnetic field is above this wire in the plane of the board. And so what that means is apply our right-hand rule, thumb in the direction of the current, curl in the direction of the magnetic field. This magnetic field here, so this is going to be B, is going to point in, like this. And so this theta hat here is really just going to be some vector that points in. Okay. So now we have our magnetic field. The next thing we need to do is calculate what the magnetic flux is. So in order to do that, what we're going to do is define some dA vector. So dA vector is going to point in. If dA vector points in, we can determine what the direction of dl is here. So this is going to be some dl vector that goes around this way. So I'm also going to say that the current goes around this way. Now, something to note here, when you're looking at these equations, the way they have this written here, this, this was a B dot dl. When you're looking at these equations here, you might confuse yourself and say, well, I have a dl here and I have a dl here. Why aren't they the same thing? Well, this B dot dl has to do with the magnetic field that's summed around this loop that the magnetic field goes around. This E dot dl has to do with the loop of wire. And so really, even though these are both written as some dl vector, these are two different dl vectors. Okay. Which is ultimately why when I was beginning to go through the process of doing this calculation with Faraday's law, I said, well, typically the way that we do this is we say if B is in here, I'm going to choose dA to be in, and that gives me the direction of dl. But I did think it was worth noting that this dl and this dl are different. Okay, so now what we can do is we can evaluate the right-hand side of Faraday's law, and this is going to say that the negative partial derivative with respect to time of the integral of B dot dA is just going to be equal to the negative partial derivative with respect to time of the integral of B times dA. Okay, so we took this dot product. So B vector dot dA vector is just going to be B dA. So we can plug in what our magnetic field is here. So this is going to be mu naught I naught divided by 2 pi r. And now we have to ask ourselves what dA is. So I'm saying that this magnetic field is going to vary with this, this radius r. So for every one of these Amperian loops that I have, if I have like a little one here, or a bigger one, or a bigger one, they're going to have different magnetic fields. So the magnetic field falls off with 1 over r as I move away from this wire. And so that's an important piece of information, because when I'm parameterizing what dA is, dA, if I say that this is going to be the x direction, is going to have a little piece dx, but it's also going to have a little piece dr. And it's very important that you're defining this little piece right here in the same way that I'm defining this magnetic field here. So you might have, if instead you wanted to call this the y direction, you could have said that this was going to be dy times dx. But since I wrote my magnetic field initially in terms of r, I'm going to say that this dA is going to be dx dr. Okay. So the magnetic field from the straight wires is B external and B from the rectangle is B induced. Yeah, that's true. But here, when we're doing this calculation, I don't know if it explicitly says it, and it's unfortunate that it doesn't. It does say it here. So part B, it says, find the current induced in the loop as a function of time, ignore self-inductance. So when it says ignore self-inductance, you're right to say that if I have some current that's going to go around here, that's going to produce some magnetic field. But because we're ignoring the self-inductance, we're ignoring that induced magnetic field. So here we're only, if I want to be really explicit, we're only concerned with the external magnetic field. Okay. So now we have this, this double integral written out here, and what I should do is I should write what my limits of integration are, and so I can put a second integral sign here because I'm integrating over both x and r. And then what I can do is I can write in what my limits of integration are. So for x, this is going to go from 0 to w. So I could be very explicit. So this is going to be x is equal to 0 to x is equal to w. And then for r, because this is moving away, for different times I'm going to have different distances here, right? Because if I start at time t is equal to 0, this is the distance d. But if I wait a little while, then this loop is going to be further away. And so what I want to do when I do my limits of integration with respect to r is to say that this r is going to be, the lowercase r is going to be d as a function of time, going up to r is equal to d as a function of time plus h. Okay, so this is getting a little messy. Let me make this a little bigger. So this is going to be equal to minus partial derivative with respect to time, integral of, this is going to be my r limits of integration. This is going to be r is equal to d as a function of time, going up to r is equal to d as a function of time plus h times the integral in x. The integral in x is going to go from 0 to x is equal to h. Sorry, what am I doing? X is equal to w. Okay. And then I have my integrand. So mu naught I naught divided by 2 pi r times dx dr. Okay. So we can start by evaluating the integral over x. So there's no x dependency here at all. And so that means when I do this integral, I'm just going to get a w out front. So this is going to be equal to, let's pull out everything that's a constant. Mu naught I naught divided by 2 pi times w times the integral of dr over r from d as a function of time to d as a function of time plus h. Okay. Now when I do this integral, and I have I left off my partial derivative here. When I do this integral, this is going to give me a natural log. So this is minus partial derivative with respect to time of mu naught I naught divided by 2 pi times the natural log of d plus t plus h. But we actually haven't determined exactly what d plus t or d of t is, the distances this function of time is yet. And the way that we can do that is to say that d as a function of time is going to be equal to the initial distance d plus the velocity times the time. Okay? So this is going to tell me that when I do this integral, I'm going to end up having some d plus v0 t plus h divided by, this is going to be divided by d plus v0 t. Okay. Now I can take this time derivative, and then that's going to help me find what the current is. I'm not going to do that explicitly, but what we will do is we'll evaluate the left-hand side. And so if I know that this loop has some resistance of R, then the left-hand side, because my dl and my I are going to be in the same direction, this says that this is just going to be I times R. And so in order to find I as a function of time, I can divide both sides by R. And so I as a function of time is equal to the negative partial derivative with respect to time of this whole term. that we have here. Okay. Also, when we did this on a previous problem, we set the lower bounds as h and the upper to h plus d. Are we doing it different here? So that might be a matter of what you're told h and d are. This lower bound, this should change as a function of time, right? So as this is moving away, the whole loop is going to be moving up. So it shouldn't just be a constant. It should be something that changes with respect to time, which is why I say that this is d as a function of time. And I determine my d as a function of time here by saying that there's some initial distance that this starts at. And then as time evolves, because this is moving at some constant velocity, I have this extra term that adds to the initial distance. So the initial distance is d plus v0 times t. Tells me that at some later time, so we can draw this over here. So this has moved up a little bit. So this is going to be d as a function of time. So the whole loop has to move up, which is why I make the limits of integration both for the lower bound and the upper bound time dependent, because the whole loop is going to move. Now, an interesting question that could be asked, and I already wrote the exam, so I can't ask this anymore. And it's probably a better question for a midterm than a final, because, like I said, I don't want to make the final too difficult. Is what's different about this if this portion right here is fixed? So this distance is always d, but then this one stretches up. In that case, what you would end up having is this would be the distance just d, not d as a function of time, and then this would be the distance d as a function of time plus h, because what we need to do is we need to parameterize the change in the distance here, and because this distance here is h, the total distance that we start with here is going to be the distance d plus h, lowercase d plus h. And then this is going to expand out with this factor here that comes from the fact that the velocity is making this loop larger. So that's a slightly different question that you could ask, where the lower limit of integration is going to be a constant. But if you're taking the whole loop and you're fixing the area of the loop so the area of the loop doesn't change, but you move the whole loop up, then the lower limit is going to be a function of time and the upper limit is going to be a function of time. Okay, Red says, would you not have initial distance d in the x direction as well? Why would you only put d in the y direction? Okay, so that's a good question. So the reason why I only have the distance d in the r direction, as I have it here, you could also define it as a y direction if you wanted to. So make this dr a dy and make this magnetic field a function of y instead of a function of r. The reason why the limits of integration with d only come into play in the y direction is because this distance d is in y, right? This is only a distance in y, as opposed to this distance w. This distance w is going to be in the x direction, but that's actually just fixed, right? Because if I'm moving this loop up, I'm not stretching it out, right? So that would be a slightly different problem that would say move the loop up and also stretch the loop out. But here, this distance in x, so this is my x direction here, is just going to be fixed, and so it's always just going to be from 0 to w, because really that's what this problem is asking. It's possible to ask a question where you say, I'm going to fix this height h, and I'm going to change the width as a function of time. Well, if that's the case, what you would end up doing is you would say the limits of integration in h are going to be fixed. They're not going to change with respect to time. But the limits in x are going to change as a function of time. And so that's really what you would want to do in that case. But it's kind of a different question to wonder what might happen if the width changes as a function of time. Okay. So Eric says, I get that it's moving up. It says that at time t is equal to 0 is the distance d away from the wire. So if at t is equal to 0, why are you starting at d and not the lower bound at the h? So this, let me draw this again. I think it might make a little bit more sense. So when I'm talking about the bounds and my limits of integration, it's really a matter of, I'm saying that this is going to be, this is the x direction, this is the y direction. But y is equal to 0 is this line. So this is the y is equal to 0 line. So where does this loop live? It lives beginning at y is equal to d. So this is the minimum distance from the positive x-axis that the loop lives at. So that's the lower limit. That's why I said that this is d as a function of time, or why I start at d. And then the reason why I say it's d as a function of time is because it moves. So then you can ask yourself, well, how far up does this go to? Because that's really what the limits of integration are telling you. Is like where does this loop start in y? Where does it end in y? And where it starts in y is going to be d, or more specifically, d is a function of time, because it's going to move as time goes on. And then it's going to go up to, because this distance is h, and this distance is d, then this total distance is going to be d plus h. And I'm mixing my uppercase and lowercase. So in the problem, I think this was all lowercase. But that's ultimately why my lower limits are what they are, and my upper limits are what they are. Okay. Follow-up question, if we were asked about how the thing is changing, would we say that it's the first case, the magnetic field is changing and not the area or its orientation? Yeah, in a sense. So this one I don't know that it really fits very neatly into one of the categories that we have, because it's not that the magnetic field is changing as a function of time. It's the magnetic field varies with distance. So the further away I am from this wire, the lower the magnetic field is. So if I'm all the way up here, I have a small magnetic field. I'm really close to the wire, I have a large magnetic field. And so the loop is going to be moving from a region where there's a large magnetic field to a region where there's a small magnetic field. So I suppose in a sense you could say that the magnetic field is changing, but it's not quite like the kind of problem that we've done before where we say, okay, well, we have some loop and we have some magnetic field that moves through this, and then this magnetic field varies as a function of time. It's really more the fact that where the loop is in the region where the magnetic field varies with distance is changing. And that's what's changing this. So I could conceivably say that there's kind of like a fourth option. So the options that we were given for how the magnetic flux can change with respect to time. One way is to explicitly have a time-dependent magnetic field. Another is to have the area change as a function of time. Another is to change the orientation, so that was like the spinning loop. I told you in the study guide explicitly, I'm not going to ask that. But the last one, well, there's one more, and that's really some combination of any one of those. But another way that you can change the magnetic field or the magnetic flux is to have a magnetic field where the magnetic field varies with some distance, and then move the loop from one place to another place. But you're not really changing the magnetic field with respect to time, and you're not really changing the area with respect to time. But what you are changing is where the loop is and how much magnetic field is going through it, because it's positionally dependent. That's another, I guess, another case that you could put under the categories of ways to change the magnetic flux. You could kind of say that it's the area that's changing as a function of time, but that seems a little bit non-intuitive, because when you say like the area changes with respect to time, you say like this area is going to expand or contract. And in that interpretation of saying that this is a matter of the area changing as a function of time, it's really the area where the magnetic field lives is changing as a function of time. So by moving this away, I'm changing what area or where the area is that the magnetic field moves through. And because the magnetic field varies as a function of distance, that's going to in turn have some time-dependent magnetic flux. So this is actually a good example of, and why a lot of times I don't like to say, if you ask me a question, is this always true, or are these the only examples of this phenomena? This kind of breaks the mold in a sense, because it's not very cleanly a time-dependent magnetic field. It's not really a time-dependent area, but it's because the magnetic field varies with distance, and because the loop is moving through a region where the magnetic field varies with distance. That's really what's giving you the time-dependent magnetic flux. So sorry if that was a little bit long-winded. So follow-up question, I think I answered this. If we're asked how the thing is changing, would we say it's the first case? Okay, yeah, that was kind of what I was trying to get. Okay, so the next one, yeah, so Eric also asked with regard to Lorentz Force Law, or I'm actually not sure, because Lenz's law and the Lorentz Force Law are two different things. But we could think about what the direction the current should go around this loop, whether it's going to go counterclockwise or it's going to go clockwise, based on Lenz's law. Because what does Lenz's law tell us? Well, Lenz's law says that the direction of the induced current is going to be such that it opposes the change in magnetic field. So the change in magnetic field is going to be some decrease in magnetic field. Remember that we had some current I0 that's going to be moving to the left here. This is going to give me some magnetic field that points in. But as I move this loop away from the wire here, I'm getting less and less magnetic field that passes through it, right? Because remember that the magnetic field varies as a function of R, right? So this was what our magnetic field looked like. And the further away I get, the smaller the magnetic field. And so we want to recover the magnetic field that we're losing, because that, in a sense, because that's what nature does. It opposes the change. And so if I'm losing magnetic field pointing in, then I want the induced magnetic field to point in. And if I want the induced magnetic field to point in, that's going to tell me that the current should flow around in the clockwise direction. And we can see why that is, because if I point my thumb, let's look at the top element right here. If I point my thumb in the direction of the current and curl in the direction of the magnetic field, that's going to give me a magnetic field that points in. And because we're losing the magnetic field that points in as I move this away, that's going to be recovering the magnetic field that I lost, in a sense, to get the current to go around this way. So that's one way that you could think about applying Lenz's law. The other is in the context of the Lorentz Force Law. And so what the Lorentz Force Law should tell you is that the force acting on this loop should be such to oppose the change. So we've already established that the current should go around this way by making arguments about what the direction of the induced magnetic field is. But we can see that another way, and that's to consider, if the current does flow in this direction, what's the direction of the force acting on this loop? So in order to do that, what we can say is dF is going to be equal to I dl cross B, where this is really B external. So point our fingers in the direction of the magnetic, or point our fingers in the direction of the current. So for the bottom piece, this points this way. Curl in the direction of the induced magnetic field. That's going to give me some force that points down like this. I can do that for every side here. So this one's going to point up. This is going to point this way. And so what's the force acting on this loop going to look like? Well, it's going to make this loop want to expand, right? Because all the forces acting on this loop are going to cause this to expand. And again, that's consistent with our expectations according to Lenz's law, because expanding the loop is going to be opposing the change, because I'm losing magnetic flux as I move away. And the loop's trying to do something to counteract that. And one way to grab more magnetic field is to expand the loop. And so that's another check that you could have for what Lenz's law would say. So the two ways that you can apply Lenz's law to check your answer from Faraday's law are to consider what the direction of the induced magnetic field is. So that was the first thing that we did. And that induced magnetic field is opposing the change because we're losing magnetic field. And this is going to be in the same direction. And so that gives me the current going around this way. And the other one is, if the current does go around this way, it's going to expand the loop. And we should expect that it should want to expand the loop, because expanding the loop is also going to be opposing the change. Okay? So other questions. So we can do any number of these. Now, things worth looking over for the exam. So things that I would definitely say look at. Look at ways that you can calculate electric and magnetic fields both with symmetry and the brute force arguments. Those are going to be highlights on the exam. So when am I allowed to use Gauss's law? When do I need to use, so if I'm calculating an electric field. So two ways to calculate electric field. One is by applying Gauss's law. The other is by, this is not an integral, this is a infinitesimal. dE is equal to 1 over 4 pi, losing grip on the chalk, chalk's getting too small. 1 over 4 pi epsilon naught dq divided by r squared times r hat. So that's the other way. And then we could also think about how do I calculate magnetic fields, both with symmetry and brute force methods. So the symmetry method is applying Amperes law. That's what we did to find the magnetic field from this, because we knew it was infinitely long. So this is going to be integral b dot dl is equal to mu naught I in. And then the brute force method is going to be b sub r, mu naught I divided by 4 pi I already have my I, so this is going to be dl cross r hat divided by r squared. So these four equations are very important. I'm not going to tell you too much else, but I will say the exam is written, and you need to know when to apply every single one of these. Okay. Now the other thing when we're talking about the ways that we can apply these is what types of problems could we do with Amperes law? So Amperes law, really the only types of problems that we talked about were problems where we had some infinitely long current, right? So the problem that I just did was an example of that. But another example of that is something where I have some current density. So for instance, if I have, and this was like the problem on the third exam, right? So third exam, I actually don't remember exactly how I read this. This had some current density J as a function of R out here, and this J as a function of R goes this way. Some I goes this way. And then additionally, I also asked what's a condition between J0 and I if the magnetic field on the outside is 0. I highly suggest looking at this problem. Can I go in some detail on DL XR hat? DL XR hat. And the problem we had. I'm not quite sure what it is that you're asking? Are you asking like when dl vector is going to be x hat dx? If this is what you're asking, then again we can look at these kinds of these four equations that I have written here, and ask ourselves what situation might we have where that's the case. Well, this goes back to the case of the first problem that I had on the third exam, when we wanted to find what the magnetic field was at the center of the triangle. We had some finite lengths of wire, and then here we had some dl vector is going to be some x hat dx. Okay, so that's that kind of naturally leads us into how we would talk about problems that we would do with the Biot-Savart law. There's really only two types of problems that I could ask about this, and again I'll hint at it a little bit. I've already asked something with straight lines, so it's pretty likely that I'll ask something about an arc, right? So I could do something like this. So current comes in, it goes around the arc here, and then it goes out like that. So what's the difference between these? Really the difference is how I write what dl vector is. So here dl vector is going to be some r, if this is some capital R, this radius of capital R, this is going to be some r d theta, right? And then you need to know how to parameterize what the limits of integration are here. I would say that if this is the angle theta, then this goes from 0 up to pi, okay? Or if you want to go the other way, this is 0 goes to pi. It's symmetric. It really doesn't matter the order that you do the integral in. Okay, so that's this guy and this guy. So we talked about everything that I can do with Amperes Law. It's really only things that are infinitely long. And again, I highly recommend looking at the question from the third exam. Biot-Savart, you can do things with finite lengths of wire, where my dl is going to be some x hat dx or some y hat dy. Or you can do something about an arc of a circle. Again, I'll say I've asked this before, I haven't asked this yet. Gauss's law. What can we do with Gauss's law? Well, we can do things with, I already told you that I'm not going to ask you something about planar symmetry. So it's only spherical and cylindrical symmetry. So you'll need to know how to apply Gauss's law for those cases. And so examples of each, we could have some sphere that's hollow on the inside, some charge density is a function of r. Find what the electric field is everywhere. We could do the same thing with something that's cylindrical. Or maybe it doesn't have to be hollow. Or maybe we could have multiple charge densities. Be able to do those. So then the last one that we have here is, it's kind of like a modified form of Coulomb's law. This one doesn't really have a name. And you know, me being as cocky as I am, I have half a mind to put my own name on it and call this Wu's law, just so that I could say this is Amperes law, Biot-Savart, Gauss, and then this would be Wu. But you know, I wasn't the one to discover it, so I'd probably get shot down pretty quickly with that. But this equation right here, which is kind of a derivative of Coulomb's law, this is the one that you want to use when you have some charge density that's going to be finite. So if it's an infinite charge density, we can use Gauss's law, and we actually should use Gauss's law because it makes it a lot easier. Or if it's some finite charge density spread over a line, then we want to use, I'll just call this Coulomb's law. Now, again, we talked about how we could do this both for lines and arcs. Make sure you know the difference between these and how you evaluate those. So in the arc, dl x r hat would simplify down to r d theta, exactly. But it's also it's not dl x r hat. It's dl vector is equal to x hat dx, or dl vector is equal to r d theta theta hat. You just want to make sure that you're careful with your notation here, because it's possible to if you define these things incorrectly to start with, you'll carry over a mistake. So if I injected an x in this, there's a big difference between x and x hat. X hat is a unit vector. X is some variable distance along the x-axis. So there is a big difference between those. Okay. What else can we talk about? Wave equation question. I think I've already basically told you what that's going to be. The first question, which is it's similar to Tatiana's first questions. I don't know how to type a vector symbol. Oh, that's okay. That's okay. First question is going to be similar to Tatiana's question, but I don't want you to just write down the integral form of Maxwell's equations. And in fact, I won't give you full credit if you just write them down. But what I want you to do is start from Stokes' theorem, divergence theorem, show how the integral form of Maxwell's equations can be written from those. And we did that in class at the end today. Other things, make sure you know how to do circuit analysis. So circuit analysis is going to be important for the time-dependent circuits. We haven't asked a question on time-dependent circuits yet because that was new since the last exam. And then there was also there's also a possibility of some type of Faraday's law question. So think about the Faraday's law, the different types of questions that we can have with Faraday's law, and that's really the whole exam. So there's I always I don't know, maybe it's a difference in when I say something's the same or when students say something the same. To me, I don't think there's really any surprises on this exam. It's in terms of material, it covers basically all of the material in a slightly different way than we've done them on the last exams. And I think that the questions that I'm asking are easier than the ones that I asked in the previous exams. Largely because of the type of geometry that you have. So there's only so many things that I can play around with, and there's only so many options that I can choose for the geometry. And I would look back at the old exams, look at the type of geometry that we've used before, and then be very comfortable using the geometry that we haven't used. We've gone over those types of questions in class and on the homework, and there have been some on the previous exams about the cross product of dl and r. Yeah, that's really important. So when you apply the Biot-Savart law, when you apply Biot-Savart, this dl cross r hat is really important. So if we were doing some, if we were going to do some something like or we could do almost the exact same thing as the question on the old exam. So on the third exam. So this is dl. If I say that the current flows around this way, this is going to be dl. This is going to be r hat. The angle between them is going to be, I can call theta. And so when I do dl cross r hat, this is going to be mag dl, mag r hat, times the sine of the angle between them, times the unit normal vector you get from the right-hand rule. So fingers in this direction, curl in this direction, this points that way. That's how you would do this for finite lines, and then it's important to parameterize what sine of theta is. Because for every different dl I have a different theta, and in turn a different sine of theta. So this needs to be parameterized ultimately in terms of the same variables that you're integrating over. And that's what we saw on the other exam. But when we do this with arcs of circles, it actually, and part of the reason why I say that some of the things I might ask are a little bit easier, if it turns out, I'm not going to tell you definitely, but if it turns out that I do an arc like this, so if I do some arc like this, well, what's nice about this is if this is dl, r hat by definition, if I want to find what the magnetic field is at the center of this half circle, r hat points from dl to the point of observation. And for every dl I have over the arc of the circle, it might not look this way because I suck at drawing these, but trust me when I say that for every dl that I have here, if dl points this way, r hat points that way. If dl points this way, r hat points this way. All of these, when I take the cross product, dl cross r hat, this is going to give me mag dl, mag r hat, times the sine of the angle between them, times n hat. But the sine of theta is going to be 1, because this is always 90 degrees. So that's something important to know, that when I'm doing B of Savart over the arc of a circle, then when I take the cross product, it's actually quite a bit simpler than when I have the straight wire like this. And that's because the sine of the angle is going to be 1. Okay? Other questions about cross product dl and r? Yeah, so I answered that one already. Okay. Exactly. So in this case, because I'm going around the arc of a circle, dl is r d theta. So if you looked at the equation sheet that I provided, I actually provided you a lot more information than you're going to need on the exam. And there's a couple of red herrings in there, in a sense, that I tell you things about spherical symmetry, cylindrical symmetry, arcs of circles. I can't possibly ask all of that. So what you're going to need to do is you're going to need to be able to identify, for the situation that I give you, is this spherical? Is it cylindrical? Is it planar? I'm not going to ask planar, but in principle, you need to be able to identify what the dVs and the dLs and the dAs are for all of those situations. I tell you what they all are, and I do it in very arbitrary terms. So for instance, I'll say something like dA is going to be equal to 2 pi r dr, or dA is going to be equal to, what else did I say? I say 4 pi r dr. Something wrong here. Something wrong here. This one's good. What am I not seeing here? This is sorry. This is going to be 2 pi r d. No, that's what I have here. I'm blanking for a second. This is d. Well, it's actually it's not a dA. It's just an a. So I say, for instance, a is equal to 4 pi r squared. Okay, there's a difference between these in some sense, and you have to be careful because they look very similar. One's for cylindrical symmetry, one's for cylindrical symmetry, but you have to know what the difference is between them. And so, which one do I use in which situation comes down to, am I talking about cylindrical symmetry, or this is really for like a circle? This is the surface area of a sphere, right? You have to know what the difference of those are. Could you show a solution of the wave equation looks like, or do an example of it? I can't really. I can think of. Let me think of something that is and is not a solution to the wave equation, because there's only so many of those that I can write that aren't what I wrote on the exam already. So what could I write? I really, honestly, I can't answer that question. Because I can't tell you exactly what's on the exam, and I can't think of something that isn't on the exam. Actually, I can. So basically, this question, there's four choices. There's four choices for what is what the wave equation is. You have four choices, and it might be. I give you more than just one option in the sense that it could be one, it could be two, it could be three, it could be four, it could be all of them, right? But you're meant to circle any and all equations that are the wave equation. So something that I could ask you that might be the wave equation, and you can tell me. Let's do par z is equal to mu naught epsilon naught par e par t squared. Okay. Is this or is this not the wave equation? So imagine I give you like four equations like this, and you have to decide whether the equation that I gave you is or is not the wave equation. This is an example of something that's not the wave equation. Why? Because the wave equation has second derivatives in space. Now this is the wave equation. But it's not too hard to write something that looks kind of like the wave equation, but isn't the wave equation. So I can change some things around here. So I could do okay, so I brought it back. This is the wave equation. I could do that. I could do that. There's a lot of little things that I could change about this equation to make it not actually the wave equation. But this, the way that I have it written right now, this is the wave equation. So the question is, can you identify this equation or not? And if you go through the notes, or you don't even need to derive the wave equation. Can I look at this and say I have some second spatial derivative acting on E that's equal to mu naught epsilon naught second second time derivative acting on E? That's a wave equation. Can it be something other than dz on the left side? Yeah, it could. It could. I could make this an x, or I could make it a y. As long as it's a spatial derivative, a second spatial derivative, and this is equal to mu naught epsilon naught times a second time derivative, that's still a wave equation. And I could do funny things like I can move this to the other side, or I didn't ask this, but in principle I could have if I wrote it like this, which is later on the way that's actually better to write equations like this, because well, this gets past the scope of things, but z is a function of x and t in this case, and then this is equal to 0. That's another way that I can do this. And what I did was I factored out the derivatives here. And what this is called something actually. This is what's called the D'Alembertian. So we've seen the gradient, right? You can have gradient squared. This is what's called the Laplacian, but this particular operator is what's called the D'Alembertian. And again, it's a little bit past something that I would ask, but there are reasons why you would want to write this equation this particular way, because then you can say that it's the operator acting on the electric field, and that's going to be equal to 0. And it's convenient to write it like this if you want to go about trying to solve this equation. So the punchline for us really is be able to identify this equation for something that I might do differently with it. So for instance, this is still the wave equation if I do this, right? I just move the mu naught epsilon naught to the other side, but this still is the wave equation. Okay. I stop when shapes start moving their way into the equation. Okay. Yeah, it's a little bit of notation. It's a little bit of notation, and it's past what we're doing here. But it's a shorthand. So why write this whole thing like this when I can express everything that's meant here by writing it like this? It's just a shorthand. It's just shorthand. But and to a point, that's kind of the power of some of the things that I've been trying to show you guys, because it's just a name. You can call it whatever you want. If you want to define some happy face operator, so happy face operator acting on E is equal to something, right? Then you just need to say, well, what is the happy face operator? But it's a lot more convenient to talk about like an operator acting on something than it is to say, well, there's a whole big long list of numbers that's associated with this, and I'll worry about the numbers. If you can think about how the operators define the type of functions that you can get out of this, which is really what we're doing when we're talking about the wave equation. There's a very small set of equations that actually solve the wave equation, and we saw one of them when I said that E as a function of z and t is equal to E0 cosine of kz minus omega t plus delta. So this is like one thing that can solve the wave equation. There's a couple other ones, and I'm asking another one on the exam that we haven't explicitly seen before, but the process is the same to show that it's a solution. You take two spatial derivatives, take two time derivatives, show that it satisfies this equation. But it's how would I say? Part of what I'm trying to do with this course and trying to get you guys to think about is how do I move past thinking about things strictly in terms of numbers and thinking about like vectors in abstract ways, and then think about what the wave equation and doing the Maxwell's equations in differential form versus integral form gets you to think about really is, how can I write an integral as a differential equation? Sometimes it's nice to do that. Sometimes it's preferable to do that. But it's kind of extending some abstractions. And I realize this can be a pretty abstract class, but I mean for it to be in some sense, because I think that's the most that you can get out of some of the things that I have to share with you guys to get you to think more abstractly. What does the answer look like when you satisfy the equation? Okay, so let's just kind of go through this particular example, because this was the one that we did in class. So what does it mean if this satisfies this equation, and under what condition does it satisfy the equation? So this is going to be mu naught epsilon naught. So in order for this electric field that I give you here, let me write it over here now. So this is going to be E as a function of z. Let's make this a z again, and t is going to be equal to E0 cosine of kz minus omega t plus delta. If this satisfies the equation, that means that if I find what the second derivative with respect to z is of E, and then also find what the second derivative with respect to time is of E, and I plug it into this equation, then there's not something weird happening where I have like functional dependencies and I would have like a singular point. It's true in general. And what that really means is when I take the appropriate derivatives of this, the functional portion of this is going to cancel out. And so let's see why that's true. And we can first start by taking first derivative with respect to z of this. So this is going to be E0 minus sine, we get a k out front, k z minus omega t plus delta. Take a second derivative of this. So second derivative with respect to z is going to be equal to minus E0 k squared cosine of k z minus omega t plus delta. Okay. Now let's do the same thing with our time derivatives. So if I take a time derivative of this, I'm going to get a negative omega out front that's going to cancel with the negative sign that I get when I take the derivative. And so this is going to be plus E0 omega sine of omega t, sine of kz minus omega t plus delta. And then the second derivative, second spatial derivative, or second time derivative really, is going to give me a minus E0 omega squared cosine of kz minus omega t plus delta. Okay, so now I have my second time derivative, I have my second spatial derivative. All I need to do is take both of these and then plug them into the wave equation. Okay, so when I plug this into the wave equation, right here I'm going to have minus E0 k squared cosine kx kz minus omega t plus delta. And then on the right hand side I'm going to have, this is going to be a mu naught epsilon naught times E0 omega squared cosine of kz minus omega t plus delta. And I see something kind of curious happening here, because I cancel out my dependency on z and on t, right? Because all of the z and t dependency is inside this cosine, right? But I have a cosine on both sides of the equation, and so what that says, I can cancel them out. Okay? So when I cancel them out, and I can also cancel another term. I have a minus E0 here, I have a minus E0 here. And then what this says is k squared is equal to mu 0 epsilon naught omega squared. And then that's the real condition that comes out of this. So in order for this to satisfy the wave equation, k squared is equal to mu 0 E0 times omega squared. And you can walk this back a little bit further, and I didn't really have time to do this, to talk about dimensionally what is k and what is omega. Well, k should have units of 1 over length. Omega should have units of 1 over time. And the reason for that is that the argument of a sine or a cosine or a natural logarithm or an exponent, it should be dimensionless. You shouldn't have any units on the inside of here. So anything that has a unit needs to multiply something else that has like the inverted unit. So we know that z has units of meters. So in order for this to be dimensionless, if z has units of meters, k has units of 1 over meters. T has units of seconds. In order for these to multiply together to get something that's dimensionless, omega has to have units of 1 over seconds. And so because of that, what I can see, if I write this k squared is equal to mu 0 epsilon naught omega squared. Let's take a square root of this to bring this around. Okay, so k is equal to root mu 0 epsilon 0 times omega. We also know from something that I said in the notes that 1 over square root mu 0 epsilon 0 is the speed of light. So this says k is going to be equal to omega divided by c, or c is going to be equal to omega divided by k. Let's apply a little bit of dimensional analysis here. C is the speed of light. The speed is going to be a meter per second. So we say, is this a unit of meter per second? Let's walk back through the arguments that we had before. This needs to be dimensionless. So when I multiply a meter times whatever k is, I need to get something that doesn't have a unit. So that tells me that k has units of has units of 1 over meters. I can say the same thing about omega. When I multiply omega times time, this needs to be dimensionless. And so if time is units of seconds, omega has units of 1 over seconds. So this has units of 1 over seconds. Let's see what we have here. We have 1 over omega divided by, we have omega divided by k. So this is 1 over seconds divided by 1 over meters, which is going to give me something that's dimensions of meters per second. And that's the real punchline here. When we're trying to compare What is this parameter k? What is this parameter omega? Why is this a speed of light? Well, if this is what the solution to this equation is, and I know that z is a unit of meter, and I know that time is a unit of seconds, then naturally this ratio of omega to k is in units of meters per second. And so that tells me, again, it points back to the speed of light, because the speed of light should be in units of meters per second. So punchline really is dimensional analysis is your friend. A lot of problems in physics or engineering or sometimes mathematics, if you're at some impasse and you're looking at something and you're like, it doesn't really make a lot of sense. Something that you can do is you can see, are the units working out? Because if the units aren't working out, then you know you made a mistake. Or in the case of what Maxwell did here, and then saying, okay, well, what are some solutions to this equation? You know something about what the units of these parameters have to be. Because the argument of a cosine needs to be zero, or sorry, it needs to be dimensionless. And the prefactor that you have here should also be in units of speed. And so because of those two things, you can deduce that k and omega should have the units that I have written here. Okay, and that's actually independent of each other, but they talk to each other. So one way to look at it is, okay, speed of light is meter per second, then this should be a 1 over seconds. This should be a 1 over meters. But then the other way to look at it is, what is the solution telling you? The solution tells you that it has to be that way, so the argument is dimensionless. Yeah. Okay. So that's going to be it, I think. So like I said, I didn't want to tell you too much, and I did stop myself because I didn't want to, when talking about the wave equation, I didn't want to give you explicitly what I was going to give you on the exam. But I did hint at things that you should definitely know how to do for the exam. Yeah, so you'll have 2 days to do it in a sense, because you get to start it on Wednesday and then finish it on Thursday. But it's better not to rely on that. I heard somebody the things. I really do love my job, but sometimes people can do things that can frustrate you. So I heard somebody say that after I said that the exam was broken up into 2 days, and that you would get to see the whole exam the first day, somebody's like, well, I guess I'm done studying. That's not a really good way to go about things, because this exam is easier than previous exams. It's not easy wholesale. So look over some of the things that I suggested looking over, and I think you guys will be pretty well prepared for it. Okay? So best of luck to you guys studying. We're going to do the mock exam tomorrow in recitation, and I'll see you tomorrow then.